This is part A of problem 63 in chapter 5. We have a 3 kilogram mass on the floor, a string over a pulley and connected to a 5 kilogram mass which is being held stationary. The 5 kilogram mass is 4 meters above the ground. It is released from rest, and the first question asks us to determine the speed of each object as the two pass each other. Well, we know as the two pass each other, the 3 kilogram mass will experience a 2 meter increase in height, while the 5 kilogram mass will experience a 2 meter decrease in height. So delta H is positive for the 3 kilogram mass and negative for the 2 kilogram mass. I've also written the quantities M3 equals 3 kilograms, M5 equals 5 kilograms. Now we know the initial velocity of each of the masses is 0, while the final velocity of the 3 kilogram mass and the 5 kilogram mass have to be the same. If they were not the same, then the string would become so tight it would break, or it would become so loose the problem just wouldn't work. These masses are moving with the same velocity, final velocity. I can write a conservation of energy equation. The total mechanical energy of the 3 kilogram mass plus the total mechanical energy of the 5 kilogram mass initially has to equal the total mechanical energy of the 3 kilogram mass, the final total, plus the final total of the 5 kilogram mass. Now, the reason I've crossed out the kinetic energy for the initial conditions is because they are initially at rest. What I'm going to do next is I'm going to subtract the potential energy, the initial potential energy from both sides, because I know then that gives me the final potential energy of the 3 kilogram mass minus the initial, which is the change in potential energy for the 3 kilogram mass. And the final for the 5 minus the initial for the 5 gives me the change in potential energy for the 5. I still have the final kinetic energy for the 3 plus the final kinetic energy for the 5. Potential energy, mg, in this case delta H, because it's a change in potential energy for the 3 kilogram mass and for the 5 kilogram mass. And then I put in the formula for the kinetic energy, 1/2 mv final squared for each of the 3 kilogram mass and the 5 kilogram mass. Time to put in some numbers. These are the potential energies, the 3 kilograms times 9.81 times the change in height for the 3 kilogram mass, that's a positive 2, plus the 5 kilogram mass times 9.81, and that goes down 2 meters. On the next line, I've put my kinetic energy for each of the masses. So when I combine like terms, I just did 3 times 9.81 times 2 plus 5 times 9.81 minus 2. That gives me negative 39.29. And when I do 1/2 of 3, I get 1.5 plus 1/2 of 5. That's 2.5. 1.5 plus 2.5 gives me 4. And I still have to multiply by the final velocity squared. So when I solve that problem, I add 39.24 to each side, and then I divide by 4, and then take the square root. I get a final velocity when they are at the same location of 3.13 meters per second, and that does agree with the answer in the book.